Hello, Chemistry 11 Honors. This is Mr. Chan. And today what I wanted to do was do a little bit of more expansion on delta H, or the change in enthalpy. Now, a couple of things that you need to consider. Recall, delta H is an extensive property. So what is an extensive property? It means that it is related to the amount of substances involved in a chemical process. So in this case, delta H is directly proportional. Now, we had talked about this in one of our calculations from before. Now, remember here, whoopsie, in this example that we had done here, remember I said that delta H was negative 890 kilojoules per mole reaction, and it changes depending on what we are looking at. So in this case, it was for 2 moles of oxygen gas. But if we were to change it to 1 mole, then this one, the value would be different. Now, the other thing is that delta H changes signs when the process is reversed. So let's say, for example, here we have half N2 plus half O2 gives you NO. It's an endothermic reaction because you are absorbing, let's say, 90 kilojoules of energy. If we were to reverse the equation, notice the sign is flipped to negative. So it would be an exothermic reaction. This again goes back to some of our basic material where we had talked about the enthalpy change for a reaction is equal but opposite in sign to delta H for the reverse reaction. So this is just something to reinforce that concept. Now, one thing with delta H, what we can do is follow something called Hess's law of constant heat summation. The overall enthalpy change for a reaction is equal to the sum of the enthalpy changes for the individual steps in the reaction. So basically, if we were to take all the energies of the individual steps and we would add them together, what we would get is the energy change for the overall step. Now, let me give you an example here. So let's say, for example, we are given 3 individual equations. I'm going to call this, let's see here, oopsie. So this would be A, B, and C. Now, those 3 equations join together to form this equation. So if we were to find out what is the delta H, what we would do is a combination of these 3 individual steps. Now, so how do we approach this? Basically, you're looking for patterns. So in this case, notice we have CLF on the reactant side, and we have CLF here. So what we would do is, if I were to take equation A, I would have 2 CLF plus O2 gives you Cl2O and F2O, and delta H would be 167.4. Now, notice we have fluorine minus 1 as reactant, and we have fluorine minus 1 as a reactant here, or sorry, F2 as a reactant here. So we have, if we look at equation C, it'll be 2F2 plus O2 gives you 2F2O, and here would be negative 43.4. Now, the third one, if we look at our products, notice we have CLF3 in our products. And here, notice we have CLF3 in our equation B. So in this case, what we would have to do is flip our equation B. So for equation B, if I flip it, I have Cl2O and 3F2O would give me 2O2 and 2ClF3. And I need to flip the sign to negative 341.4 kilojoules. Now, how do we combine this? What we do is we cross out similar chemicals from both the reactants and the products. So if they're on opposite sides of the equations, we cancel it out. So in this case, I have oxygen, oxygen, cancels out these two oxygens here on the products. We can cancel out 3 F2Os here, here, here. And the other one is the ClO2, Cl2O. And what we're left with is 2 ClF plus 2 F2 gives you 2 ClF3. And if we were to combine all of the delta H's together, what we would get is we would get a negative 217.4. Now, if you notice the original question, the coefficient is 1 to 1 to 1. Here you notice it's 2 to 2 to 2. So what we need to do is multiply everything by 1/2. And what we get is we get ClF plus F2 gives you ClF3. And in this case, we get negative 108.7 kilojoules. So this is what Hess's law heat of summation talks about, where when we add up all the individual steps, it equals to the total for the overall equation. Okay. Now, the other thing I want to talk about is something called the enthalpy or heat of formation, delta HF. And what this is the formation of a compound from its constituent elements. Now, basically, the idea is how much energy a compound requires or releases when it's formed from the individual elements. Okay. Now, one thing for you to be aware of is the standard heat of formation. Standard heat of formation is the formation of 1 mole of substance in its standard state from the elements in their standard state. Now, what do I mean by substance in the standard state or elements in the standard state? Is basically what form of the element or compound that would exist at 1 atmosphere or 298 kelvins. Okay, and generally the most stable form of the element is used for the formation reaction. Let me give you an example of what I mean by this standard heat of formation. So let's say we were to form alcohol, C2H5OH. What it is it's formed by carbon in its natural state, which is graphite, hydrogen, which is a gas, notice here the phase symbol gas, and oxygen, which is a gas. Now, so that's what I mean by the elements in their standard state, because at 1 atmosphere or 298, hydrogen exists as a gas, oxygen exists as a gas. Now, when we talk about heat of formation, the most stable form of any element in its standard state is 0 because no formation reaction is needed. And this gives us a theoretical starting point for delta H. Now, what do I mean by this? So if you take a look at your appendix number 4, what you will see is you will see this table. And what I've done is I've highlighted specific ones for the formation or for the heat of formation. You notice aluminum is 0. Bromine is 0. Notice those are considered 0 because in their standard state, aluminum would be a solid at 1 atmosphere and 25 degrees Celsius, while bromine would be a liquid. Same thing with calcium. Calcium at 1 atmosphere and 25 degrees Celsius, it would exist as a solid. This is why we would consider it 0. Okay. Now, Carbon is special because carbon, what happens is there's two forms, one that is graphite and one that is diamond. Graphite, you could think of it is like the carbon that you get when you burn a piece of wood. That would be considered coal or graphite. Diamond, notice the heat of formation of diamond is not zero because carbon in the diamond form has to undergo high temperature and extreme pressure. And so that's why the heat of formation is not zero for diamond. You do not burn a piece of wood and get diamond. No, that's not its natural state. Okay. Now, so one can calculate the heat of a reaction by taking a look at all the energies of formation of the product and subtracting it from all of the energies for the formation of the reactants. Now, in this particular case, I state the formula right here. In this case, you need to know how to use. Okay, you will be given this formula. You don't have to memorize it. You just need to know how to use it. Now, you might say, what is this En? So En, what it is the sum of all the stoichiometric coefficients. Now, what do I mean by this? It says use the value of delta HF in Appendix 4 to calculate the delta H for the following reaction. Now, one thing to correct, this is a gas. Okay, so we have silicon SiCl4 liquid plus 2H2O liquid would give you SiO2 solid and 4HCl gas. Now, so how do we calculate delta H? So we take delta H of the reaction is equal to the sum of delta H of the products minus the sum of all the delta H's of the reactants. So in this case, what that would be is I would take all my SiO2 plus 4 times HCl minus SiCl4 plus 2 times H2O. And so we just look at Appendix 4 and we find that silicon oxide, where is silicon oxide? So this would be negative 911 plus 4 times HCl, which is a gas. If we look for HCl gas, is negative 92 minus, I'm just going to put in the second line here, negative 687 plus 2 times water. Water is a liquid. Let's see, where's water is a liquid, is negative 286. Okay. So what we get is, let's see, 911 and 4 times 92. So I get 1279 minus 687 minus, here would be negative, oh, sorry, here this would be negative 1259. And so what I would get here is I would get positive 20 kilojoules. Okay, that's what the delta H would be like. Okay, so this is using the summation. So in this case, this summation formula to calculate delta H. So there are different ways of calculating delta H. We've done some from the other class, but this one is using the heat of formation for each of the different compounds, add them together to figure out the heat of reaction for the overall reaction. All right, folks, thank you very much. Have a good day. Bye-bye.